Good morning. The first thing I have to tell, I'm not Vittoria. Yeah? And I was lucky because I was in the room of Alfredo when he realized that she wouldn't come. So he invited me to present one lecture, and I'm very pleased to do it. So the topic of my lecture will be optimization with linear complementarity constraints. And should I say that it's a topic that I've been working for more than 30 years. So it's not too old, but it's still, you have still a lot of work to do, as you can see later. Okay, so the outline of my talk will be, I'm just going to present definition, then formulations and applications, then finding a feasible. There are three important issues here. The first one is to finding a feasible solution of the problem. Then the second one is some sort of stationary point. Then from the stationary point, using this stationary point in order to find global minimum. So and then I just make some comments about computational performance of the algorithms and then some current and future work. I'm not going to present many details, but I'm going to just switch to the ideas. Yeah? So I'm trying to be fast and at the same time try to explain what is really important in this problem. Okay, so first of all is to define the problem. That's the most important thing. So as you can see, we have a function, which usually is continuous differentiable, sometimes second differentiable. And you have linear constraints, these equalities, which are nice. Then the second group is also, everything is linear. And because QY is a polyhedron, so it's made of linear constraints. And then you have this complementarity condition. Okay, so the difficulty will be not the function, not the constraints, linear constraints, but the complementarity condition, okay? So, and this makes the things difficult and makes the problem NPR. So now you have to face an NPR problem. So you have problems, yeah? Fortunately. And then what you can distinguish is two sets which are very important. The first one is what I call the linear feasible set. That is the set of the linear constraints, okay? This you can see, you can check whether it is feasible or not by solving a linear program. So this is solved, okay? Finding a linear feasible solution is easy, okay? Now the feasible set is what I call the generalized LCP, and this is ANPR. So when you try to find a feasible solution, you have to face an NPR problem, okay? And then you have feasible solution, which means that you have linear feasible plus complementarity. And complementarity means what? You see, xt omega equals 0, x and omega are non-negative. This means that for all I, x, y, and omega I must be 0. That is, when you have one positive, the other one must be 0, okay? These variables are called complementary, yeah? And they are really difficult to handle. Okay, the more general case, you can assume that in some applications disappears, that people call it mixed. Yeah, because they have some unrestricted variables xi, and the corresponding complementarity variables are 0, okay? Then a special case is this one where everything, I wouldn't say everything, but at least finding a feasible solution will become easier. Then the linear case, this is the most important as far as the applications is concerned, but nowadays it's appear a lot of problems which are nonlinear. The function is also nonlinear, particularly quadratic. Okay, and then in a new extension that comes just a few days, and it is an extension where the xi are non-negative and the omega i's are unrestricted, okay? I'm going to show one example. And this could be the starting point. Actually, it has been the starting point already for another problem, which is different from the one that I'm going to do. And I'm going to present this at a future work, okay? So I'm going to give an example of this one just to see that this problem is also important, okay? So let me put an example. That's another thing which is very important to understand the problem. Okay, so we have a function which is linear, then we have these nice constraints because this one, x1 plus y1 greater than equal 1, if you introduce a slack variable, it becomes equality, okay? So you have this very, very nice form, which is exactly the form where I present before. The matrix E is this rectangular matrix 1, 0. The matrix M is 1, 1. And then you have N, and you have these constraints, and you have the complementarity between two variables. If you draw it, you can see this is the linear feasible set. This is a convex, a very nice convex set, okay? But then the feasible set is just like this, which is non-convex. So the problem is always a non-convex problem, okay? NPR, non-convex, very good. So very difficult, very interesting, because very nice structure, okay? So what I'm going to try to show you, actually this is the global minimum here, yeah? And if you just relax the complementarity constraint, the global minimum is there, okay? Okay, so the global minimum of the relaxed problem is different from the global minimum of the problem. And as I can see, what I'm going to show you how to solve this problem. Okay, not this particular one, because this one has been solved, but just bigger ones, yeah? Okay, so application formulations. Okay, so all these sorts of formulation, that is what I've been doing is just, not only me, a lot of people have been doing, is just choose some of these problems and transform them into MPLCCs, okay? And why do you do this? Because you don't know how to solve them. So what you do, you try to put in this form in order to solve them. It's not just for joking, it's just because you need it, yeah? And all these problems are very important. Non-convex quadratic programming, bi-level programming is a very important problem nowadays. Bilinear programming, absolute value, 0-1 integer programming, is not so important to transform, but you can do it. This famous linear complementarity problem, the eigenvalue complementarity problem, that's a problem that's been working recently very hard. A fractional quadratic program, which I'm going to show you. The total least squares, I'm not going to show, but you can believe me, this can be transformed in this one. So it's a special case of this problem. Optimization with cardinality constraints, a very important problem nowadays, like sparse programming, compressed sensing, all these problems come with this condition. Condition number, that is the estimation of a condition number of a non-singular matrix. This is very important in numerical terms. And also these problems in graphs, which are very difficult nowadays, and people have been working very hard on this one. Very important people working on this thing, and it is clique number and independent number of a graph. All these problems have many applications, so you have many applications here. But if you need more applications, then you have more applications, okay? All these problems are just, in all these problems have been just formulated as pure MPLCCs, like games, market equilibrium problems, traffic equilibrium. Whenever you have equilibrium, you have complementarity, most of the times. Okay, so production and market decision problems, contact problems, that's very important application. Robotics, telecommunications, I'm from a telecommunication institute. Finance, that's very important applications in finance, and machine learning. And you can see all these sorts of applications, or at least some mentions of these problems in these beautiful books of Cottle, Pang, and Stone in '92, more recent to Lu, Pang, Ralph, and I forgot to put another one, Pang and Fakinei, and also Ralph, who did a very good survey paper that appeared in Royal Society, okay? Okay, so let me just mention two very fast formulations. The first one is bi-level problem. So you have a leader here, and you have a solver there, a follower there. So the leader gives some ideas, at least just orders, to the follower response, okay? So what you do, you can transform this one, this is a linear program, on X, okay? You can put Y for this side, and you get a linear program. And you know that solving a linear program is the same as having primal feasibility, dual feasibility, and complementarity, okay? So if you do this, you get the problem, okay? So you have function, this function, this is the constraints of the leader, and the other one is just linear programming, okay? The duality, this is duality, 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 okay? This is primal feasibility, dual feasibility, actually dual feasibility, primal feasibility, and complementarity. Okay, so this is the problem where the matrix, look at this matrix, is positive semi-definite. This is the case which I said before that it's easier, okay? Because this matrix is hemisymmetric or skew-symmetric, and because it is skew-symmetric, it's positive semi-definite, okay? So you can have all sorts of generalizations, but if you have, for instance, constraints on the leader level on X and Y, the problem becomes more difficult, okay? So another question, another interesting problem which introduced the new problem is this one. Suppose that you have a quadratic function and you want to minimize, globally minimize this function, not finding a local, but
just a global, okay? And that's interesting because actually this idea comes from the eigenvalue complementarity problems, okay? So what you do, you put lambda dense one, and then you make some easy calculations. B should be symmetric, positive, definite, and you get this problem. Okay, this is a parametric problem on lambda, okay? And what you have to do is to find the MPLCC where omega is not restricted to be non-negative, okay? So the complementary XT omega does not mean that for all I, XI omega is 0. So this is a more difficult problem because you don't have this very beautiful property, but you still have a lot of work to be done with this problem. And to be honest, this is one of the most important interests in the current interest which I have got now. Okay, so this is, as I can see, as you can see, this is a parametric. So you have to find the smallest value, lambda, of this MPLCC where omega has no restriction, okay? So let me mention some algorithms. I don't have much time, but then let me see that there are three important issues, as I said before. The first one is to finding a feasible solution, okay? And in order to find the feasible solution, if you have this nice property, any stationary point, look, I repeat, any stationary point of this quadratic function on the linear constraints give the solution. Okay, so this case is where finding a feasible solution is very easy, okay? So because you only have to find a stationary point, not a global, just a stationary point. The stationary point, either it is feasible and you have, if it is infeasible and the MPLCC is infeasible, or the minimum is 0 and you get a solution, a feasible solution, okay? But in general, so you can use active set methods, whatever you want, or projective gradient or interior point methods, whatever you want. Or actually, you can use transform into absolute value programming or other techniques. Okay, so the thing is, in most of the applications, you look at the problem, you play with the structure of the problem, you get a feasible solution. In all of the applications which I mentioned before, usually this happens. That is, you just play, you just look at very efficient algorithm. You should be clever, obviously, and you will need to know something about research. But if you do this, you can find a feasible solution. So usually, what I'm saying, that finding a feasible solution for most applications is not so hard. But suppose that you cannot do it, then you can use a global optimization method, okay? And this is more difficult, yeah, because you have to find a global. But there is a very interesting property, which this one, I'm not going to the details. You can do this by using some sort of enumerative algorithm that exploit this beautiful property of for each y, xi is 0, omega is 0, so you can branch, okay? And you can find stationary points in each node, okay? So you can do this. And the beauty thing of this one is this. That is, whenever you get a stationary point in one particular node, which is 0, then you get a solution. So it's easier than a global optimization because you know, I always say this to everyone, and probably some of the people that are staying here have heard about that whenever you have a global optimization and you know the objective function, optimal object, you don't know the function, the solution, but you know the optimal objective function value, the problem becomes computationally more easier, okay? Because you see, you have another stopping criterion. You know that in global optimization, the problem is not to find, most of the time, not to find the global, is to see that it is the global, to show this is the global. That's the most difficult part. Because here you don't need, you have another criterion. That is, you have another criterion that says, okay, if you get a stationary point of one of these, in one of these branches where satisfy this value 0, then you have done. This is very good. The problem is, as you can imagine, when there is no solution, okay? Because if there is no solution, you never get this stopping criteria. So you never stop. Yeah? So you have to branch. So this is the thing which I present here. You can use this enumerative method, but you can also use any sort of quadratic optimization, global quadratic optimization algorithm, but you can also transform into integer program, okay? That's a nice construction. That is what you do. You just use the problem, you transform the complementarity conditions into 0, 1 constraints, okay? And then you have this property. First, this problem is linear feasible, okay? Second, it is feasible. and it is linear feasible. And another one is if there's a feasible solution, not the global, if you have a feasible solution of this linear program with alpha positive, with the objective function positive, that's the opposite. Now you need someone which is positive. If you get this one, you get a solution. If you don't have, then you have to maximize this problem to be 0. So again, if you have a solution, it's much easier than when you don't have a solution, okay? Because you only have to maximize when you don't have solution, okay? So just move to the global and stationary point. That's the problem again. So that's the constraint set, okay? So that's the GLCP. Global is defined as usual, and the stationary point is defined as usual. The problem is to find this condition, okay? Because this set is non-convex. Because this set is non-convex, showing this is very difficult, okay? And this particularly difficult where this solution is degenerate. That is, there is at least one I such that both complementarity variables are 0. So one thing that you should realize that complementarity problems are much more difficult when you have degenerate solution. But it is not surprise because linear programming also has the same property, okay? So what the people did, you say that's difficult, okay? That's difficult to show this one, so try to get something easier, like some type of Kkt conditions. So there are two definitions which have been used for many people. One is strongest stationary point and another one is M stationary point. And as you can see, this is Kkt type. Kkt type. So it's good for algorithms. Algorithms like Kkt conditions, yeah? Actually, the Kkt conditions are very important because for the algorithms, it was really good help for them. Without Kkt conditions, nobody could solve problems, yeah? So now you are happy because you have some sort of Kkt conditions, and what you can show is that if you have a strongest stationary point, then it is a M stationary point, and M stationary point, if you have a stationary point, it is M stationary point. Another thing which is if you have a non-degenerate solution, all these stationary points are the same, okay? And another thing which is very important, wherever you are global, you have an M stationary point. But you can have a global which is not a strong stationary point. So what you do in practice, that's very interesting. What you do, you try to find the strongest stationary point, but usually you terminate in M stationary point, okay? Because if you terminate in M stationary point, you know that global implies M stationary point, okay? And the algorithms that I propose, that's just an example, so just to verify, is what I call complementarity active set method. And this is an extension of the active set method that maintains complementarity in each iteration and terminates, I would say that strongly, but now I have proved that this algorithm terminates in M stationary point, okay? And this is very good because you can use some sort of code if you have the source code, and you can transform the minus into, or other code into this algorithm in a very efficient way, okay? And for the linear case, then this is a basic restrictive simplex method, okay? And it's easier, okay? How does this work? Just 2 minutes, very easy. Okay, so the difference between this one and the complementarity just applies for linear functions, okay? Linear simplex method applies for linear programs. So basis restrictive simplex method applies to linear case for the MPLCC, to the LPLCC. Okay, what you do, and you suppose that you have a basic feasible solution of the linear constraints of the GLCP, so you consider the set of non-basics in 3 categories, then you have a very nice stopping criteria. That is, either you get a non-basic variable, like in simplex method, either you get a variable that can increase, like in simplex method, or you get a M stationary point. So you have solved it. Okay? Either you have a variable to increase, or you have a M stationary point. So if you don't have a M stationary point, you increase a variable, and you replace with a basic variable, like in simplex method, and you get another basic solution. This example shows clearly. Suppose that I have this solution here, okay? That's a basic feasible solution of the constraint set, of the linear constraint set, because it is an extreme point. Okay, so what you do, you have non-basic variables, basic variables, and you have this set. So the criteria is not satisfied because we have this negative, so you can increase the variable x1, omega 1. So omega is 0 as increased to a value 1, and you get the point, the new basic solution, which is this one. And this one, as I show later, I showed before, this is the global minimum. Actually, this is an M stationary point. Okay, so the basic simplex method, this is some people that people don't know, is, or didn't know before, is that the algorithm terminates always in M stationary point, which is good, okay? So because as I said before, whenever you have a global minimum, you have a M stationary point. Okay, so let me change to global methods. So the first one is the branch and bound algorithm, which is probably the most popular, and is very similar to the branch bound method for the 0-1 integer program. Okay, the idea is you just design a tree similar to the enumerative method. It is based on the complementarity variables, okay? In each node, you create two nodes by fixing two pairs of complementarity variables. In each iteration, what you consider relaxed program, okay, and you find a lower bound. Whenever you find an upper bound, you update it, and the algorithm stops when there is no lower bound in one particular node, which is smaller than the best upper bound. In this case, the upper bound gives the optimal solution. This is terrible. To be honest, this is terrible because never finish, yeah? But the problem is you can improve. Why? How you can improve it? By doing two things which are important. First, to get good methods for finding good upper bounds. Because if you find good upper bounds, the algorithm tends to stop earlier. And second, which is most important one, is to find good algorithms. And it's very difficult to find good algorithms to find good lower bounds, okay? And the combination of these two gets an algorithm which can be more efficient. And what people have done is, that's the algorithm, okay? So suppose that you have the solution again. So in the same problem, so LP1, you have the relaxed LP, okay? The optimal solution is this point there, okay? So it's not complementarity, okay? So you have to branch, but you are branched by 1, 0 to 1, 0. Here, you get the optimal, okay? The upper bound 2, that's the best upper bound. The other one, the upper bound is 4, so this one is bigger than this one. You don't have more nodes open, and you stop. That's good because you have only pair. So suppose you have a lot of them, never finish, yeah? So that's not very good. But people have done a lot of work, very recent work, particularly on STP and RLT techniques, also other ones. Actually, I've been working as well in this area. But you see, the most important development are STP and RLT, and that's very good combination of them, sometimes works very well. So what people are fighting in order to find better lower bounds. I'm not going to consult, but let's see, this is positive semi-definite, so you can ask me if you want, reformulation RLT, so it's again, okay, and another approach is to transform again your MPLCC into a 0-1 integer program, okay? What you do, you consider this combination, but you have to introduce a big value here. And this is the drawback of the problem. So what you do, instead of solving this one, you solve the 0-1 integer program with a parameter theta, which should be fixed. Because if it is not fixed, it will be a nonlinear constraint. Also, what you do, you fix it by usually 1,000, whatever, and you try to solve. Well, the problem is, as you can see, is that theta should be given a priori and may not even exist. And even when they exist, it's very difficult to tune it. Usually it works very well with 1,000. I always say to people when they start with this type of research, just the first thing to do is just to solve the MPLCC as 0-1 integer programs. Because you have a code. So you can see your models. Suppose that you have a model and you want to see the results. So the best thing to do is to transform this one into a 0-1 integer program and solve it. Okay? When you do this, what you do, you have some idea about the quality of your model. Okay, so another thing which I really like is the same thing as I've explained. It's just transformed this problem into a parametric GLCP. Okay, so I have to find the smallest value lambda, satisfying the solution of this one. When you put the function here and you just update this lambda. Okay, so there are three important things here. One is solution of the GLCP. The second one is the updating. And then the last one is to terminate. Because whenever you see, in order to update, usually you can do it. Solving this when there is a solution, remember I said, when you have a GLCP, when you have a solution, it's easier. But the problem is the last one, when you have to terminate, the last one has no solution. And show that the GLCP has no solution is difficult, very difficult. So as I can, that's the algorithm that works for this case, very, very easy, yeah, very well. Okay, so to do, just start with this point. You can find this point, which is the M stationary point, and we immediately realize when you put this constraint, the set becomes empty, okay? As you can see, it becomes empty. And because it is empty, then the previous one is an epsilon global, usual. It is a global, actually, in this case. Okay, so some hints about computational performance of the algorithm. Branch and bound is not good, but if you add this one, as I said before, improve. Now, the sequential usually is efficient to find the global, okay? Usually it finds the global, but the problem is that to stop, you need to show that the last GLCP has no solution, which is quite difficult. So it's difficult for this algorithm to give a certificate optimality. Okay, now then I didn't talk about this one. That 0-1 linear program usually work well, and you should try when you have a small problem, because you have a code, so you can use Cplex or whatever in order to solve this problem and have an idea about your models. But as I said, it is the problem in this case is not only 0-1 integer program is not a very good problem to solve, despite you have a lot of pre-processing techniques and cuts and things like that, that becomes much more efficient nowadays, but you have to tune the theta, and tuning the theta is not so easy. But let me say, which is very interesting conclusion, that usually this integer program gives a better certificate of optimality, which means that you can combine integer program with sequential. This is what we have been doing lately, yeah? So combining these two, okay? Finish. 30 years is too much for half an hour, yeah? So I've been working during 30 years on this kind of problem, so far half an hour is too little. Okay, so current and future work, computation at better lower bounds for branch and bound algorithm, STP and RLT, and valid inequalities and cuts. I have been working more on RLT, but I also, that's one thing which is interesting, believe me, that is my suggestion is, if you want to solve, just apply STP at the beginning and forget about branching. This is my experience. Because STP does not improve when you go down, usually. This is my idea. But RLT is better in certain way. Why? Because you have some drawbacks, the same drawbacks as STP, that is the increase of the number of variables that starts from n to n squared. But the problem is, the better is that if you use RLT, you can use linear programming code. As you can see, as you know very well, linear programs codes are much better than STP codes. I think that in order to be very honest about this, you have to improve a lot on STP codes. You are still in beginning of the way. But I like very much STP. STP is a very important problem, and I really like because they have a very beautiful structure. So I would say that to combine this one with branch and bound and also with sequential complementary. So actually, I always say this to people. When you try to solve problems, combine. Don't just use your algorithm, because usually it does not work. Just use this one, another one, put another thing, and try to be innovative in the way of combining this algorithm. This is very important in order to get good algorithms. Okay, so you can improve sequential by finding more efficiently. You can use penalty functions. Actually, this is what we have been doing. Interior point algorithms I have been doing as well as this one. Try to find a better certificate for optimality. This is most important and most difficult part. And then the extension to a convex quadratic function, we have been doing this before. Recently as well. So other algorithms for solving parametric, not the sequential but other ones, that's some idea which is still open, that is how to solve this parametric problem, which I mentioned before. And finally, remember the new problem which I mentioned, that is, suppose that you have omega y variables are unrestricted, the problem becomes more different at least. I wouldn't say it's more difficult, but at least it's different. And then application of MPLCC. Thank you very much.